Welcome to the L2 Applications webcast of Group 21. The long-term effects of using fossil fuels as the world's main source of energy consist of rising temperatures and extreme weather, and rising sea levels forming a threat to the natural habitats of wildlife. Therefore, renewable energy is becoming increasingly important as a means of achieving a sustainable carbon-neutral future. A clean and efficient form of generating energy is wind. Most wind energy comes from turbines. It is our goal as engineers to design and build the most efficient wind turbine. Let's start by outlining the design brief. The wind turbine should be a horizontal axis design, rotating clockwise from the wind direction with maximum tip-to-tip diameter of 450 mm, and it must be manufactured as a single part by 3D printing, fitting in a box with dimensions 400 by 150 by 100 mm. The maximum angular velocity should not exceed 3000 revolutions per minute, and the maximum power coefficient (CP) should be obtained at a tip speed ratio between 3 and 8. The turbine should reach its maximum power coefficient at a stated design TSR in a range of wind speeds 6, 8, 10 and 12 meters per second. Let's consider the aerodynamics. Firstly, we had to decide on the number of blades of the turbine. We have chosen a two-bladed design because a one-bladed design includes a counterweight, resulting in a more complex design as well as requiring higher rotational speed to yield the same energy output. A three-bladed design would significantly decrease the maximum possible radius of the turbine, reducing the advantage of blockage effect in the wind tunnel. The optimal tip speed ratio for maximum power extraction is inferred by relating the time taken for the disturbed wind to re-establish itself, Ts, to the time required for the next blade to move into the location of the preceding blade, Tw. The maximum power extraction occurs when the two times are approximately equal. However, as the length of the disturbed wind stream S varies from case to case, determination of TSR optimal is not by analytical calculation but rather empirical. We initially assume S to be half of the turbine radius, which yields a TSR optimal of 6.28. With simulation results from Q-Blade, we eventually chose TSR is 3.7. The tip of the blade experiences a higher linear speed and Reynolds number compared to the root. By estimating the range of Reynolds number, a CL/CD against angle of attack polar graph is plotted with data from dozens of airfoils analyzed by Q-Blade. Among all of them, E216 and AH7476 have outstanding CL/CD over a wider range of angles of attack such that the performance of each blade section will not be greatly penalized under structural deformation. There are some sections, like E63, that have a higher CL/CD at certain conditions, however their performance decreases rapidly as angle of attack and Reynolds number change. AH7476 has a higher peak of CL/CD compared to E216, however with the same chord length, its cross-sectional area is smaller. Since the maximum aerodynamic force and centrifugal force are applied on the root of the blade, the thicker airfoil E216 is used on the inner side and AH7476 is used on the outer side of the blade. We have chosen a thin elliptical wingtip ensuring a smooth transition of the flow. We have also chosen an elliptical nose cone because of its simple design, and the nose cone itself does not produce significant aerodynamic advantages. Let's dive into the structural analysis. We have written a code which analyzes the flow field around the turbine as input for the structural calculations. We started by discretizing the blade into 100 sections. The local wind velocity and Reynolds number experienced by all sections were estimated, which was used to determine the design values of the lift and drag coefficient from airfoil tools, data and graphs. Accordingly, we have chosen to calculate the optimal chord length using the Smidge optimization formula because it is based on the more detailed and sophisticated model of the flow in the rotor plane as compared to the Betz formula. The optimum twist angle was then found using an iterative numerical method based on the beam element theory, where the blades were idealized as a cantilever beam. The sectional structural properties, such as the moments of inertia about the principal axis and the coordinates of the centroid, were found using a function for polygeometries. Subsequently, the aerodynamic lift and drag forces and the centrifugal forces at each section were calculated. Using simple bending theory, the maximum stress and moment distribution along the blade could then be plotted. From the graphs, the maximum experienced stresses were found, which were not close to the tensile yield strength of ABS M30 plastic at any section, therefore confirming our choice of airfoil sections. Finally, a code was written to calculate the maximum tip deflection using the unit load method. We found that the maximum deflection was 0.655 mm and therefore not significantly affecting the aerodynamic performance of the turbine. Q-blade modeling. Q-blade has a built-in function of optimizing the chord length and twist angle of each section of the blade for some specific tip speed ratio. The results calculated by Q-blade were then used to verify the calculations done by our code. In the final design, the dimensions of the blade, optimized by Q-blade, were used. Modeling by Q-blade is an iterative process. The maximum power coefficient of the blades, which are optimized for a range of tip-speed ratios, are compared, and among all of them, at a tip-speed ratio of 3.7, the power coefficient is the highest. This is also positive for structural considerations because a smaller tip-speed ratio leads to a lower centrifugal force under the same wind speed.
We opted for a folding nose cone design to maximize the tip-to-tip diameter while meeting the design constraints. Both halves of the nose cone were folded together via a built-in hinge and glued after printing. A set of teeth on the mating surface located both halves. Splitting the nose cone at a right angle created more contact surface area and kept the main incident surface of the nose cone smooth to reduce drag. The hinge was of a simple ball-and-socket design, with as much clearance as possible between the moving parts to minimise the chance that the hinge would get fused together during printing. The external face of the hinge was also shaped to follow the contour of the nose cone, and the entire hinge was designed to be as small and discreet as possible to minimise its effect on the aerodynamics of the turbine. A small 1mm diameter rail was also added to the trailing edge. There was some worry that the 3D print would be unable to capture the most thin parts of the aerofoil. Therefore, the rail helped provide an outline of the trailing edge for the print to aim for. As our design used two different aerofoils, they had to be blended together. Although stall was accounted for in the calculations of the twist angles, there was still some worry that in practice the aerofoils may suddenly stall at different points, and therefore produce unanticipated loads on the blade. To try and mitigate this, small bumps analogous to whale tubercles were incorporated into the region of transition between the two aerofoils, as seen here. A further discussion on the aerodynamic advantages of these features is provided later on. The folding nose cone was fully integrated with the blades as shown. The inner aerofoil section was already cleared to withstand the loads through earlier structural analysis in MATLAB, and this method of integrating the blade ensured as much of the turbine as possible was contributing to the aerodynamic performance. Clearances of at least 0.3mm, the printer resolution, were allowed for everywhere, including in the hole in the nose cone for the hub to fit into during testing. To manufacture our turbine, we first started with the hub. An aluminium workpiece was placed into a CNC lathe, and G-code to form this piece into a cylinder with the required dimensions was uploaded to the machine. The result after turning was a cylindrical piece, with a hole in the centre to eventually become the keyway for attaching to the testing rig. Using a CNC lathe increases the accuracy of the job, as human error in tooling is removed. The next stage involved using CAD/CAM software to create the correct G-code to mill the cylindrical piece into our hexagonal hub. The hole for the grub screw was also machined here. Again, using a CNC mill here offers a distinct advantage as it increases the rate at which parts are manufactured. Tool changes, for example, are very quick and efficient. Lubricant is required at all stages to keep the aluminium cool. As the tools are moving quickly, friction generated can melt the aluminium and cause build-up on the tool as well as ductile tearing on the surface. The edges of the hub were then deburred using a file. The hexagonal hub was then pared off the workpiece using a lathe again, leaving the almost completed hub. The final stage of this process was to etch our group name onto the hub, again using a CNC machine with G-code already prepared. Using a CNC mill here was crucial, as this process required high precision. The final hub now only needs a keyway. This was stamped through later on. The 3D print was largely successful. The hinge printed really well, allowing the two halves of the nose cone to slot together. To reduce friction drag over the blades, the surface was sanded to remove printing artifacts and to ensure it was as smooth and slippery as possible. This was achieved by starting at a very coarse sandpaper to remove large printing defects, and then increasing the fineness of the sandpaper until the whole blade surface was smooth to the touch. The rail on the trailing edge was also sanded off, making sure the trailing edge did not become sharp so that the flow would leave smoothly. The two mating faces of the turbine were also sanded, cleaned, and then glued together into the final turbine assembly. The additional surface area offered by the interlocking teeth on the edge, as well as the orthogonal surface of the nose cone, ensured maximum glue surface contact so that the assembly wouldn't fly open during testing. After waiting a week for the glue to cure, a final sanding of the nose cone was completed to make sure it too was as smooth as the blades, and to remove any dried glue residue from the surface. Designing the turbine, we explored biomimicry to improve the performance. We found that research in a combination of fluid dynamics and biomechanics explored how and why tubercles found on whale fins made rotary devices more efficient. CFD showed that these tubercles can increase lift and decrease drag at the same time. The tubercles focus the flow between the bumps via complementary vortices, creating high lift regions where the flow stays attached. These regions have significantly higher stall angles. Unlike other wings, which may stall violently and potentially damage the machines they're employed on, tubercle wings will always stall gradually. Therefore, in our design, we have made use of this technique and incorporated it in the transition of the two chosen airfoils to reduce the chance of sudden stall. Sadly, circumstances prevented us from revolutionising the renewable energy sector and saving the polar bears. But here is how our turbine should have performed. A maximum power coefficient of 0.4 at a TSR of 3.7, it would be able to achieve maximum power coefficient for all wind speeds. It would withstand all loads during testing without significantly deflecting or braking.
And it would not stall unexpectedly due to tubercle features.